Picture this. You've got a massive Monday meeting, right?
Oh, yeah.
And you drop this chaotic, messy spreadsheet into an AI. You type, summarize this, and you just expect absolute magic.
Right, like it's just going to solve all your problems.
Exactly. But instead, it confidently hands you completely hallucinated numbers.
Yep.
Like it gives you a revenue projection that it makes zero sense because it entirely failed to realize that the column labeled Q3 Revenol V2 actually excludes international sales.
It happens all the time.
Today, we are looking at a groundbreaking new paper that proves exactly why the smartest AI in the world turns into a bumbling intern the second it faces real-world data. Welcome to the Deep Dive.
Thanks for having me. Because, we constantly hear that AI is on the verge of fully autonomous data analysis.
Yeah.
But there is this hidden bottleneck that the tech industry really doesn't like to talk about.
Yeah, they gloss right over it.
They do. We expect these systems to act like veteran data scientists while completely ignoring how much of actual data science is just pure, frustrating human detective work.
Which is why today's source material is so fascinating for you guys listening. We are unpacking a state-of-the-art generative AI architecture paper that introduces a brand new benchmark called LongDA.
That stands for Long Document Data Analysis, right?
Right. And alongside it, a testing framework called LongDA. Our mission for this deep dive is to explore this new obstacle course.
It's a really necessary obstacle course, too.
It is, because it exposes the exact mechanical reasons why current AI agents fail at messy data and the surprising skills they actually lack.
Exactly.
So whether you are trying to use AI to clean up your own messy spreadsheets or you just want to cut through the relentless hype, stick around. We are revealing the true frontier of AI reasoning.
So to appreciate what LongDA accomplishes, we really have to look at the artificial environments where AI models have been tested up until now. Because, honestly, the grading curve has been incredibly generous.
Oh, totally. Like grading on a massive curve.
Right. Prior to this, the standard was benchmarks like DS1000.
Looking at the documentation for those older benchmarks, they are essentially sterile laboratory environments.
Yep, very clean.
They test the AI using tiny, pristine data sets. We are talking maybe 20 columns of data accompanied by a very short, perfectly structured readme file. And it explains exactly what every single variable means in plain English.
And in that sterile lab, the only real challenge for the AI is writing the Python code to execute the math.
Right.
It just reads a clean instruction, writes a script, and outputs a number. But anyone who has ever touched a corporate database or, a government data set knows that is a fantasy.
A total fantasy.
The actual bottleneck in real-world data analysis is almost never the code. It is navigating massive, heterogeneous, contradictory documentation.
Oh, absolutely.
You're dealing with hundreds of pages of code books, methodological appendices, survey design documents. You have to figure out what the data even means before writing a single line of Python.
Okay, let's unpack this with an analogy, because testing an AI on those old benchmarks is like testing a chef by handing them perfectly pre-chopped, pre-measured ingredients in little glass bowls.
I like that analogy.
Right. But real-world data science is like dropping that same chef into a wild forest and telling them to forage for their own mushrooms.
And identify which ones are poisonous.
Exactly. And they have to catch a wild boar before they can even think about turning on the stove.
And that realization that foraging in the forest is the actual test of intelligence that is the entire foundation of LongDA.
They wanted a real test.
Yeah, the researchers didn't want to test the chef in a kitchen anymore. They decided to build the ultimate unmapped forest to see if these large language models could actually survive.
And they didn't just invent synthetic fake data to build this forest, right? They went straight to the source of the most complex, rigorous, and notoriously dense data on Earth.
The United States government.
The U.S. government. They curated raw data files from 17 real national surveys across 6 major federal agencies.
We are looking at massive data pools from the CDC, the National Science Foundation, the Census Bureau.
The heavy hitters.
Right. This is the exact raw data that dictates federal policy and public health initiatives.
And the scale of the mess they handed to the AI is staggering. The average length of the documentation attached to these surveys is 263,000 tokens.
Which is huge.
And some of them reach over 735,000 tokens. Just to visualize that for you listening, think of a token as a chunk of a word, maybe a syllable. 735,000 tokens is roughly the length of the entire Lord of the Rings trilogy.
And it isn't a narrative story.
No, definitely not.
It is hundreds of pages of acronyms, data collection methodologies, and variable definitions.
Think about the worst, most confusing corporate handbook your HR department has ever handed you. Now multiply that by 1,000.
Sounds like a nightmare.
It is. That is the raw text we're asking the AI to ingest just to understand the column headers.
And to evaluate if the AI actually understands that text, the LongDA benchmark features 505 real analytical queries.
Real queries, not fake ones.
Right, these are not random math problems generated by another algorithm. The researchers extracted these queries from 30 actual expert-written publications that were based on those exact national surveys.
So these are the exact questions that human economists and public health experts spent months answering?
Exactly. And the grading is brutal. The benchmark doesn't accept a conversational essay where the AI can kind of bluff its way through.
No bluffing allowed.
None. It requires either a single number, like finding an exact 14.2% obesity rate, or a strictly formatted list.
Which forces a very specific kind of precision. But wait, hold on. If these queries are pulled directly from published expert papers, why not just let the AI search for the final published PDF of the CDC report, find the statistic, and spit it back out?
This raises an important question about the methodology.
Oh, lay it on me.
The researchers actually anticipated that loophole. They instituted a strict blocking protocol.
So the AI can't cheat.
Right. The AIs are intentionally completely blinded from seeing those final publications. They're handed the raw, unformatted data files and that novel-length documentation, and they are given the question. That is it.
Wow.
They have to independently reproduce the expert's results from scratch.
So it forces the model to perform actual multi-step data science rather than just regurgitating a memorized fact.
Exactly. But throwing an AI into that environment barehanded would result in an immediate failure.
Sure, they drown.
Current models simply aren't built to natively hold 700,000 tokens of complex tabular data in their working memory and manipulate it flawlessly.
So they had to build a massive scaffolding just to give the AI a fighting chance, which is where the second half of this paper comes in. LongTA.
The TA stands for tool-augmented.
Right. It's the baseline framework they engineered to let the AI interact with this massive data forest.
The core engine of LongTA operates on what is called a REACT loop. That's reasoning and action.
React, got it.
It is an autonomous, iterative workflow. The AI doesn't just read the entire document once and then attempt to write a master script.
That would never work anyway.
Right. It is allowed to interleave its actions, mirroring human trial and error.
Okay, so it can execute a search, read a paragraph from the manual, reason about what that paragraph implies, write a quick Python script to check the data set, realize it got an error message, and then go back to search the manual for a different keyword.
That's the exact loop. And to facilitate that loop, they equipped the AI with an incredible arsenal of specific tools.
Oh yeah, looking at the list, they gave it a redoc tool to scan pages.
Yep.
They gave it a search stock tool, which performs exact keyword matching. And they built a specialized retriever tool.
That retriever tool is a critical piece of engineering. It utilizes a BM25 lexical search.
Okay, let's translate BM25 for a second because that sounds like a textbook buzzword.
Fair enough.
Instead of just looking for the exact word income, like hitting CTRL-F on your keyboard, it's doing something more complex with the text, right?
Exactly the right way to look at it. Instead of a rigid exact match, the BM25 algorithm splits those massive documents into overlapping chunks of text.
Okay.
It then looks at the mathematical frequency and distribution of words. So if the AI is searching for household earnings, the retriever can find relevant paragraphs, even if the government manual specifically used the phrase family financial intake.
Oh, wow. So it allows the AI to search conceptually.
Yes.
Plus, they gave it a notes tool to act as a digital scratch pad so it doesn't forget intermediate steps, and a save code tool. So it is basically an open book exam, and the AI has been handed a highlighter, a stack of sticky notes, a conceptual search engine, and a Python terminal.
It's quite the toolkit.
Yeah.
But providing those tools highlighted another mechanical problem: file heterogeneity.
Meaning the different types of files.
Yeah, government data sets are a nightmare of different file types. You have PDFs, plain text files, raw Python scripts, and massive CSV spreadsheets.
A total mess.
If the AI is jumping between these, it can easily lose its grounding.
But the researchers solved this with a brilliantly nerdy feature. They built a unified document representation into the framework.
It's very clever.
They forced every single file type to parse into a single cohesive format. If the documentation is a PDF, the framework automatically splits it into manageable pages.
Right.
If it is a raw text file, it splits it into numbered lines, and if it's a CSV spreadsheet, it splits it into numbered rows.
And this standardization is crucial for evaluating the model's reasoning.
How so?
Well, whether the AI is reading a user guide or looking at a data table, it has a uniform way to cite exactly where it found the information.
Oh, that makes sense.
It can state in its internal log, I found the variable definition for age brackets on PDF page 12 and the corresponding raw data on CSV row 400. It completely prevents the model from hallucinating sources.
Okay, so we have the ultimate obstacle course in LongDA, and we have the survival kit in LongTA. So who actually survived the forest?
The results are pretty wild.
Looking at the showdown between the smartest AIs on the planet, there was a definitive runaway winner, GPT-5.
The dominance of GPT-5 in this benchmark cannot be overstated. It achieved a nearly 95% coverage rate.
And just to define that for everyone listening, coverage rate means the AI successfully followed the strict formatting instructions.
Right, formatting is key here.
If the query asked for a list of 3 demographics, it actually provided a list of 3 demographics rather than crashing, timing out, or, spitting out a conversational paragraph.
Beyond just surviving the format requirements, it achieved about a 69% match rate.
Which means it arrived at the exact, mathematically correct number that the human experts published, within a tiny 5% margin of error, almost 70% of the time.
Given the sheer complexity of the data, nearly 70% is a massive technical achievement.
It really is. But the rest of the pack struggled to even stay in the race.
Yeah, they really did.
The open source models, like DeepSeek-V3.2, hovered all the way down around a 53% match rate, and other models, like GLM 4.7, completely fell apart.
They got trapped in these infinite repetitive loops.
Just going round and round.
Exactly. They would query the same useless keyword over and over again, completely inflating their token usage, wasting hours of compute time, and never arriving at an answer.
But what's really illuminating is unpacking why GPT-5 won. It was not because it possessed some superior savant-level coding ability, right?
Not at all. What's fascinating here is that the heat maps in the paper that track tool usage reveal a very specific behavioral pattern. GPT-5 won because it was a vastly superior searcher.
The visual data on this is striking. GPT-5 heavily spanned the search doc tool right at the very beginning of the process.
Yes, before it wrote a single line of code.
It spent its time aggressively hunting for variable definitions, mapping out acronyms, and just understanding the terrain. Then, when it finally transitioned to writing code, it wrote large, highly efficient blocks of Python.
It gathered all its ingredients first, organized them, and then cooked the meal.
Going back to the chef analogy.
Exactly. It demonstrated a strategic intuition for human documentation. It knew it had to translate the human concepts into data variables before the math would work.
But that insight leads us directly to the most fascinating and, frankly, the most counterintuitive finding in the entire study.
Oh, this is the big paradox.
Here's where it gets really interesting for you all. The models that were explicitly engineered to think harder, the ones designed to spend massive amounts of compute time reasoning before they actually perform significantly worse.
We need to look closely at DeepSeek-V3.2 thinking.
Okay, break that down.
This is a model variant specifically instructed to generate long internal reasoning traces. It is programmed to be cautious, to double-check its logic, and to be highly methodical.
Which sounds good on paper.
Right. You would logically assume that in a complex 700,000 token needle-in-a-haystack problem, spending more time thinking would yield higher accuracy.
But the data proves the exact opposite.
Completely the opposite.
The standard baseline DeepSeek model got a 53% match rate, but the thinking variant dropped down to 47.8%.
And it wasn't because it gave up.
No. It used an unbelievable 36 million tokens and took 9 solid hours to run the benchmark.
9 hours.
9 hours of computing just to get the wrong answers, more often than its faster, less thoughtful counterpart.
Understanding the mechanism behind this failure is vital. Explicit, cautious reasoning actually penalized the AI.
Why, though?
Because it was programmed to overthink, it caused the AI to drastically overuse its search and retrieval tools. It kept looking for more and more context, pulling in more and more paragraphs of the government manual just to be safe.
Oh, I see. It's like a detective who is so paranoid about missing a single clue that they decide to bag up every single piece of trash at the crime scene.
That's a great way to picture it.
Eventually, their evidence locker is so completely stuffed with irrelevant garbage that they can't find the murder weapon they already collected.
That is exactly what happens algorithmically. Large language models rely on an attention mechanism to determine which words are important.
Right.
If you pump the context window full of 100 pages of irrelevant survey methodology, the mathematical weight the model can assign to the actual correct variable definition, the needle gets completely diluted.
It literally loses focus.
It buried itself in its own thoroughness. It overwhelmed its own context window and started hallucinating variables because it had too much information to process.
It proves that simply throwing more compute or thinking time at a problem doesn't magically solve it, especially if the model lacks the high-level strategic intuition of knowing what information to safely ignore.
And knowing what to ignore is perhaps the most advanced human skill in data science.
Definitely.
Which brings us to the nuances of the data queries themselves. The researchers found that the structure of the required answer completely changed the model's success rates.
Yeah, they categorize the queries into two types, right? Finding a single number or producing a list.
Yep.
The match rate for finding a single number was about 50.9% across the board. But when the AI had to produce a list of numbers, that match rate plummeted to an abysmal 28.8%.
The mechanism behind that drop-off is working memory and logic chains.
Okay, let's walk through that. Finding a single number is often a direct path, right? Find the variable, run the average, output the result.
Exactly. But let's look at what a list query actually demands. Say the query asks the AI to find the unemployment rate for white males, aged 18 to 24, in urban centers versus rural centers.
Okay, lots of conditions there.
Right. The AI has to find the specific variable for race. Then it has to find the variable for gender and hold that in its working memory.
Without losing the first one.
Yep. Then it searches for the age bracket variable, then the geography variable, finally the employment status variable. It has to filter the data set, group the variables correctly, and calculate the list.
Wow, that is intense.
It requires multi-step computation. Every additional step, every new variable definition it has to hunt down is another opportunity for the logic chain to break.
Like a weak link in a chain.
Exactly. If it misunderstands just one acronym out of those 5 variables, the entire final list is mathematically incorrect. Multi-step reasoning over long documents remains a severe algorithmic bottleneck.
But, amid all these struggles with long documentation, there was one huge, fascinating exception in the data.
Oh, the NSDUH survey.
Yes. We established that longer documentation usually confused the AI and diluted its attention. But then there's the NSDUH survey. That stands for the National Survey on Drug Use and Health.
And the documentation for the NSDUH survey is an absolute behemoth.
It's huge.
It sits at over 700,000 tokens. Based on the mechanical trends of the benchmark, every single model should have failed miserably on it due to attention dilution.
But they didn't.
No. Across the board, the models performed surprisingly well on this specific data set.
So if the detective's evidence locker was that massive, how did they consistently find the weapon?
The answer lies in human intervention. The researchers noted that the public microdata released by the agency for the NSDUH survey was uniquely prepared.
How so?
The human data scientists at the agency had already done the semantic heavy lifting. They included pre-coded variables that were derived from the messy raw fields.
Oh, so instead of the AI having to read a manual to figure out how to combine 3 obscure survey questions about drinking habits into a single metric, the human researchers had already created a clean, summarized column called binge drinking frequency.
Precisely. The humans translated the chaotic real-world concepts into clean mathematical columns.
They did the translation for them.
Yep. Once the AI used its search tools to find the name of that pre-coded variable in the documentation, the actual mathematical computation was incredibly easy. The pathway was cleared for it.
Let's distill all of this down because it fundamentally reframes how we should view AI capabilities right now.
It really does.
The bottleneck preventing AI from automating data analysis isn't the math. It isn't the Python coding ability.
No.
The bottleneck is the human context. The AI desperately struggled to understand which variable means what in the real world.
Exactly. It cannot natively navigate the idiosyncratic, messy, entirely unstructured ways that humans write manuals, define terms, and organize their thoughts.
It just doesn't think like we do.
If we connect this to the bigger picture, LongDA provides a very sobering reality check for the industry. Even the absolute best state-of-the-art model in the world, equipped with a highly sophisticated suite of search and execution tools, only arrived at the correct answer 69% of the time on real-world government data.
Which means if you are a policymaker drafting legislation or, a CEO making a multi-million-dollar quarterly decision, you cannot trust that output without manually verifying the steps.
Not at all. A 31% failure rate is catastrophic in the real world.
It's massive.
We are a very long way from an AI acting as an autonomous, reliable data scientist. The reasoning capabilities are genuinely impressive, but the reliability required to navigate complex, human-generated environments without rigorous oversight is simply not there yet.
It really makes you look at that messy spreadsheet sitting on your desktop a bit differently. It is not just rows and columns of numbers, it is a direct reflection of human logic, which turns out to be incredibly hard for a machine to parse.
It's a very human mess.
Which leaves us with a really provocative thought to mull over as we wrap up this deep dive.
I'm ready for it.
If the absolute smartest AI models on the planet are currently failing because they cannot figure out how to navigate our messy, human-written documentation, maybe the future of AI integration isn't just about throwing more compute power at the models to make them smarter.
Well, that's a good point.
Maybe it is about fundamentally changing how we, as humans, document our knowledge to make it AI ready. Think about it. If you were designing a corporate database or writing a methodology manual today, knowing an AI was going to be the primary entity reading it, would you still write it for a human reader, or would you structure it entirely for a machine search tool?
Wow. We might be approaching a paradigm shift in how human knowledge is permanently recorded.
It is a massive shift to think about. Thank you so much for joining us on this deep dive into the LongDA benchmark and the realities of AI reasoning. Keep questioning the data, keep double-checking those AI summaries, and we will see you next time.